going to see the strain displacement matrix as well as stress strain relationship in one-dimensional bar element. Let us consider this is a one-dimensional bar element. At node number 1, let us say the displacement would be Q1. At node number 2, let us say the displacement is equal to Q2. So in the last session, we have defined that the displacement function Q would be it is a function of shape function N1 Q1 plus N2 Q2. So there would be two shape functions exist here. So those two shape functions can be expressed here. Okay, so this would be the displacement function, and here I know that that N1 is called as a 1 minus zeta by 2, and where N2 would be equal to the 1 plus zeta by 2. So we substitute that the displacement function Q can be written as it is equal to the 1 minus zeta by 2 into Q1 plus 1 plus zeta by 2 into Q2. So this would be the displacement function. This displacement function will be valid at node point 1 as well as node point 2, as well as it can be valid throughout the element from 1 to 2. Wherever you take, this displacement function will be valid. So now let us try to define now what would be the strain. So the strain can be defined as it is equal to the strain can be defined as epsilon can be defined as change in displacement divided by the original displacement. Okay, so change in displacement to the original displacement. So here the dou u by dou x will be giving that it is called a strain for the given one-dimensional bar element. So dou u by dou x can be different, can be write as by using the chain differential formula. It can be written as dou u by dou zeta into dou zeta by dou x. So from this one, the strain can be defined as dou u by dou zeta into dou zeta by dou x. So now let us define now what is a dou u by dou zeta. Okay, so the dou u by dou zeta, before going to define the dou u by dou zeta, here I have defined that the q is equal to 1 minus zeta by 2 into q1 plus 1 plus zeta by 2 into q2. So here sometimes I can express that the q would be the displacements, and also the displacement can also be expressed in terms of the u. So q or u both are same. So therefore I can able to write down that u would be equal to the 1 minus zeta by 2 into q1 plus 1 plus zeta by 2 into q2. So if you differentiate this one, this dou u with respect to the dou zeta, this can be differentiated as minus q1 by 2, and here this can be plus q1 by q2, sorry, plus q2 by 2. Okay, so this is the value of the dou by dou zeta. So now let us substitute here. So therefore the epsilon can be written as it is equal to the dou by dou zeta, that will be defined as minus q1 by 2 plus q2 by 2. So into d zeta by dx. So the d zeta by dx can be defined as from the local to global coordinate system. So from that one, it is the value of 2 by x2 minus x1. So at this point of time, let us consider that the dou zeta by dou x will be 2 by x2 minus x1. So therefore, if you write down here, it can be written as 2 by x2 minus x1. So this would be the strain formula for the one-dimensional bar element. So here it is possible to write down this in terms of the, let us write down that the epsilon can be written as here. So let's give me the simplification form for this one. So the epsilon can be written as it is equal to the q1 times of, or it would be, let us take that it was minus q1 by 2. So therefore I can able to take here it as a minus q1. Okay, so this is minus q1 plus q2 divided by the 2 into 2 by x2 minus x1. So this would be the strain formula for one-dimensional bar element. So one-dimensional bar element having a node of 1, 2. So here 2 get cancelled, At null number 1, I have assumed that x1, at null number 2, it is x2. So therefore, it is possible to say that the x2 minus x1 would be called as it is called length of element. So this is called as a length of element. So the length of element can be represented as a small l. So therefore, the epsilon can be written as it is equal to the minus q1 plus q2 divided by the x2 minus x1. So this can be written as x2 minus x1 can be written as 1 by L and 1 by L times of minus q1 plus q2. So now I can able to write down that in terms of the matrix, therefore it can be written as 1 by L. So this minus q1 plus q2 can be written as in terms of the column matrix, therefore I can write down q1 q2 as a column matrix. So therefore I can able to write down as a row matrix as a minus 1 comma plus 1. So if you multiply this, what is that? The first one row, two columns, and two rows, one column. If you multiply this one by 2 into 2 by 1, you're going to get the above equation. So it means that I've transformed this linear equation in terms of the matrix form. So here I can able to write as epsilon is equal. I can able to say this would be called as a B matrix. So the B matrix into the displacement matrix Q. So here the B is called as it is equal to the 1 by L times of minus 1 comma 1. So this is a strain displacement proportionality matrix. This matrix is called as a strain displacement proportionality matrix, proportionality matrix, proportionality matrix. So the Q is called as a displacement matrix for a bar element, and it should be a column matrix only. So the Q is called as it is called displacement matrix, displacement matrix. So once you know the stress can be defined as stress is equal to the Young's modulus into a strain. So this can be written as Young's modulus is equal to the capital E, and strain can be written as it is equal to the B matrix into the Q matrix. So this is a formula that is useful to find out the stress in a given bar element. So for a stress in a given bar element formula can be used as n smallest into B matrix into Q matrix, where B is called as a strain displacement proportionality matrix.